All right. Apologize, I seem to be losing my voice today. But please take a few minutes and see if you can figure out what test you're going to need for the function that's on the board. All right, so you've had a few minutes to think about this particular problem here, and we've asked you to figure out what test cases you would need for this function. Does anyone have any test cases they think are needed? Yep. Okay. All right. Yep, that's a great test. We definitely need that one. So we need to have a test specifically for the base case. This is absolutely critical in a recursive function, is that you need to make sure your base case actually, produces the value you expect. So the easiest one is base. I'm going to use the list abbreviations because I'm being lazy. Now, we said empty list. Well, if we want to pass an empty list, actually all we need to do is pass empty. And then it doesn't matter what n is. We'll say n is 2. And we expect that to produce 0. Right. What other tests should we have? Okay, that's a good one. So we actually need quite a few, though, to test here. So what I would do is I would have, we've got a test for when the list is empty. We only need one of those. But now we want to deal with the second condition here, where it's saying, the question is, the first element of the list is less than n. So I would have one test for a number that is less than n being at the front of the list, one test for a number being equal to n, and one test for the first of the list to be greater than n. Because you really want to make sure that we are going into that condition only when it is actually true. So we could do some real quick ones here. So there's the case where n is going to be greater than or equal, or sorry, greater than the first element of the list. There's one for when the first element of the list is equal to it. Right. Now, I would do one more test. These are all very simple. We're only ever going to get really as far as comparing the first element. Well, in these lists anyways, because all the other ones are greater than n. I would give one more test. Because if you give these are great white box test cases, but they're not really good black box test cases, because these two actually have the same output. And I mean, that one's useful, but not that useful. This one's okay, but it's not great. I would now give one real sample use of this function. We've got all the boundary ones. Now let's give one real use. And that would actually make a really good example, because you want the tests to serve as both checking your code, but also providing the user with a good, here's how you use it. So in this case here, we're summing these three. All right. Any questions about the tests here? Couple things then to remember. Your examples actually count as tests. You need to give for each function, you have to have at least 2 examples. Make sure that whatever examples you choose are not something trivial. The point of the examples is to take your user by the hand and say, look here, user, see here, this is how you use the function, and this is how you can expect the result to be. Yeah?
So for the first 4 checking steps, we put this under a test column, the last checking step we put under examples.
So what I would put under examples is we need 2. So I would put this one here, and I would choose one like this one here. So when there are no elements, because these 2 together are actually form a very good description of how the function behaves. And then I would put the remaining 3 under tests. Yeah. Yeah?
Does that mean that if all the codes are used, like there's no black boxes after you run the program, it's good?
So part of
So does it mean that if all your tests runs all the codes in this function, like there's no black highlighted after you run it, and it's good?
Yes. So the black highlighting, what it is code that has never been actually executed. If you run all of your tests and you see no black highlighting, that means that everything actually has run through. But generally speaking, you shouldn't use that as a I have done enough tests. maybe you haven't really caught all the examples. Maybe your code goes through every, actually executes everything, but maybe you haven't done enough black box test cases. Because that black highlighting is really meant to show you white box. It doesn't really show you, do you have sufficient black box test cases? So it's not quite enough just to make the black highlighting go away. All right. Now, is this something that you could be expected to actually have to do on an exam? Absolutely. On an exam, we may give you a function just like this, and we may actually ask you, hey, write the test cases for it. So do get some practice with that. All right, now, the previous lecture, the clicker machine was broken, so they didn't have to do clickers today, but we still did the questions. So I try to make sure the two classes are the same. I'm going to guess and say you forgot yours today because you look suddenly relieved. So we will do the questions, but there won't be any clicker marks for them because the machine in the other section was broken. So we will do this. You can shout out the answer. How about that? So what does ADT stand for? Shout out the letter, not the... Okay, what is it? This is where everyone's like, crap, what is this again? And you're going to rifle through the slides and realize it's not in it. So what's the answer? It's A. A stands for abstract data type, which is something that will follow you throughout computer science, and if you go out into a programming background, you'll be talking about them forever. I know it's very tempting to say E. The only automotive dancing troupe I know of is the ones in the Grease movie, and if you've never seen it, it's the weekend. Go entertain yourself. It's a very strange group of people dancing around a car. I don't understand that one. Anyways. One more then. So what is in a dictionary? I hear a lot of people saying B. The answer is B. A dictionary contains key value pairs. All right. Those are all the clicker questions that we had that you don't have to do. All right. A few announcements then. So first off, assignment 4, if you haven't gotten started on it, I would. Assignment 4 does have recursion on it. It's going to be mostly simple recursion. I can say any function we ask you to write will be simple recursion. And then assignment 5 will be coming out tomorrow. It's all ready to go. And it will also be recursion, but just more complicated recursion problems. We have assignment 6 ready very shortly to come out as well. But that's dealing with weeks away, and you don't care because, is it not next week is reading week, but the week after or something like that? So, 5 times. The other thing is, of course, don't forget A0. I know that, from what I understand, the 3 people who haven't submitted it didn't submit any other assignments. So, I'm going to assume they dropped the course. Maybe they went down to 115 because, I don't know, it's easier. All right. So we left off last class, we started talking about ADTs. And remember that these ADTs, what they are is they're descriptions of different ways that we can work with data. It's saying, how do we create it, how do we destroy it, and how do we actually interact with the data? And abstract data types, there's so many different ones. There are things like binary search trees, which we'll be talking about later on. There are lists. Yes, lists are ADTs. There are vectors, there are maps and hash maps. There are dictionaries, there are graphs. There are many, many different kinds of ADTs. And what they are is ways that we can view and interact with data. It's ways that we store data. And how you think about these ADTs as building blocks. So you have some problem. In the last class, we used the example of you want to be the next person to make Amazon. And you know you've got to find some way to store that product database. And so you sit there and you think about, okay, how are people going to interact with the product database? Are they going to be adding things? Are they going to be removing things? Are they going to be changing things? Or are they going to be searching for things? And you realize, yes, people are going to add things, but it's not going to happen very often. People are going to remove things, but very rarely, because you only generally remove something from Amazon's list if it's a product that they don't want to have associated with themselves. Like maybe you're trying to sell a ghost in a vacuum cleaner, which is fine for eBay, but that's not fine for your website. So somebody posts it and you want the ability to remove it. So it's rare. But what you really want people to be able to do is search for things. So then you go to all of the available ADTs and you ask yourself, which of these ADTs most closely matches what I'm anticipating users and people in the back end, their behavior with our data set. And you realize, oh, a dictionary is actually a really good idea because a dictionary has this key value pair. The key in this example would be the name of the product and the value would be the product record. So things like the reviews, the price, the inventory, all of those things would be associated with the value. And then you know that you do need the ability to add things to the dictionary, but removing is going to be very rare. The real thing that we want to be able to do is find elements. So we want the ability to look up. So a dictionary is a really great idea. Now, what we haven't really talked about is how do you actually implement this magical dictionary, ADT. A very, very interesting thing about ADTs, and I keep referring to them as building blocks, is because you can build other ADTs from ADTs. So for example, I can implement a dictionary using a list. I can implement a dictionary using arrays. I can use a vector. I can use a map. I can use a tree. I can use a graph. I could make a dictionary out of any one of those things. Should I make it out of all of those things? Probably not, but you could. So these ADTs are kind of building blocks that you can piece together in such a way that it best fits your problem. And that's something that gets covered a lot more in things like 136 and 240. You'll start to see how these pieces actually go together. So for our situation, we are going to implement our dictionary ADT using another ADT known as an association list. And what's interesting is you've actually already seen this, we just didn't call it an association list. We called it a payroll. We called it our taxes owed. It's a list of two-element lists. So we've given you a data definition here for our association list that we're going to use in this next example. And it is either empty or it is a list that contains key value pairs, where the key is a number and the value is a string. There we go. That's an association list. We can make a dictionary out of this. Now, if you wanted to visualize this, if sometimes visualizing the list structures helps you, there's a little diagram here, and you could have, if you wanted, actually drawn these inside these boxes. Both notations are actually equivalent. All right. So now that we have an association list, how do we write it in the contract? Well, once you have list abbreviations, it's going to be somewhat tempting to not create data definitions. We're always trying to type less characters, so having to make the data definition, it's more work. And we do have a simple way we could use this in a contract. We could just say a list of list num str. Once you have list abbreviations, which I believe you're allowed to use on assignment 5, not in 4, sorry. Yeah?
I'm sorry. Like, is that equivalent, like, saying this is a nested list?
No. So you actually want to use the word nested list in a contract?
Yes.
Yeah, you can't do that.
Or then can I describe it in the definition of the function?
It sounds like you should probably show me what you've written. We'll talk later, okay? All right. So you could say a list of list num str, but my problem with using this, even though it is correct technically speaking, is that if I use that in the contract, it's not really telling me, the user, much information about this particular function. I simply know that this function consumes a list of num stir lists. But I'm not going to take that contract and map it to the fact that, oh, this is an association list function, which is why you should still do the data definition and use AL, our short form for the association list, in the contract. Because I'll see that AL and I'll be like, this is a function for association lists. We don't have any other way in Racket to let our users know what types of data is being passed into these functions and what type of data is being produced by these functions. So when you have an opportunity to be very clear or very specific or very user-friendly, you should take that when it comes to the contract and the purpose and so on. So of course, once we then get our data definition for our association list, we can use that in our contract as such. And with every data definition, we should probably also make a template function as that little bit of extra hand-holding to help our users and other developers to understand exactly how we are anticipating you're going to use this particular data type. So here we have it, our association list template. If the list is empty, of course, you're going to do one thing. Otherwise, we're going to look at the key and the value for the first element and combine it in some way with the results of doing something to the remainder of the association list. Now, I don't like this template. I don't like this template because when I look at this template, I see first, and second first. Now, there are comments here that would try to help me clue into the fact that first is the key and the other one is the value. But you know, it's still kind of ugly. So there is another way that you could actually write this contract up, and you've seen me do it before, but I'll do it over here in Racket. I love it when Racket freezes. It's like my most favorite thing ever. You're all sitting out there thinking, oh, commercial software, it always works. No, it doesn't. So let's open up the file I have. Well, we don't need that file open right now. So let's make another way that we could actually do the data or the template for an association list. Well, first off, I'd like to be a little bit more verbose about what an association list contains. So I'm actually going to create a data definition for an entry. There. And now I could define my association list. I cannot spell, so if this is spelled wrong, I apologize. Oh, doesn't that look so much nicer? It's starting to read a little bit more in a human fashion. And now we can create our template for an entry. That's dealing with the key. And that's dealing with the value. Great. Now I can write the template for the association list. And it looks mostly the same. There. I've encapsulated each entry in the association list as its own data type. So I can refer to those by their name. Instead of having to say a list of a num and a stir, I can say an entry. And that's so much more understandable because I'll be like, oh, an entry. That's a key value pair. I could have just as easily called this key value pair or pair. There's many different names that would have worked. And now in my association list template, I know that I'm doing something with the first entry and combining that with the results and doing something to the remainder of the association list. Both templates, by the way, are correct. I think you know which one I prefer. All right. So, now let's start to implement these functions for our association list so we can actually create our dictionary. The most important part of an association list is the ability to look something up based on the key. So I want to look up, hey, what is the value for this particular key? In this case, maybe we're mapping student numbers to your name. So I want to find out who 20067780 is. That's me. But if I wanted to do that, I want to look it up based on the key, and I want it to produce the value. Okay, so we can start to write some different tests. So I'm going to look up key 2 in this association list. And key 2 exists, and so it produces the value associated with it. But what do you produce if there is no entry in your list? So for example, since I am no longer a student anymore, even though I technically still have a student number, and if I were to enroll as a student again, that would be the number I would have, I'm not enrolled in this class. So if you searched for me in this class by my student number, what do you produce? You need to produce some kind of value to indicate that this does not exist. Now, here's one of the really, really fun things about a language like Racket. In languages like C and Java, functions can only return a single type. If I tried to write a lookup function in C and the values were strings, my function lookup would have to produce a string. So I would have to make some special string set aside that could be no valid value to indicate this thing doesn't exist. But do you really want to have that restriction on your data set? Well, Racket's interesting because in Racket, you can return whatever the hell you want. You can have a function that returns a string if the input value is 0, a symbol if the input value is 1, a number if the input value is 2. You can return anything. And so what we're going to do in this lookup function is if the entry exists, produce the string value. And if it doesn't exist, we'll produce false, a Boolean, to indicate it's not here. That way, every possible value is allowed. We're not restricting the values. But the question then becomes, how do you show that in the contract? So you'll note here there's no contract, but we've given you the implementation. Lookup is a simple recursive function. What we're going to do is, if the list is empty, the item isn't there, so produce false. Otherwise, we have a second base case where the first item in the association list is the item we're searching for. So if the key of the first item is equal to the key I am searching for, I produce the value of the first item. No more recursion, hence why it's a base case. Otherwise, if this current item is not the item I'm looking for, I'm going to search for this key in the remainder of the association list. Very simple function. How do you write the contract? Now you might be tempted, you know what the arguments are. It's a number and an association list. But what's the produced type? You might say any. Technically, that's true. And technically, I could say any produces any. But that's not very precise. In fact, that tells me absolutely nothing. That's garbage. What I want is I want to give a precise answer. And it needs to be precise because I want my reader to know exactly what kind of values they can anticipate are being produced by this function. Suppose they are writing some code that's going to use the lookup function. They would need to know what kind of value lookup produces. So if you are not precise, then they wouldn't have any way of knowing how to handle the values produced by lookup. So we actually have a way of representing multiple possibilities in our contract, and that is this any of syntax. And you could, and in this case, what we would do is because we are either going to say string, if the item exists, and you might be like, oh, well, it should be string or bool. That's true, but true is never produced. So the most precise contract for this function is num association list produces any of string false. Because true is not going to be produced by my function. So if you have a function and it can only produce a natural number, and to be specific, it either produces 1, 2, or 3, you could say the function produces a nat. But then the user is going to assume it can produce any natural number. And if your function can only produce natural numbers 1, 2, and 3, then a more precise contract would say any of 1, 2, 3. Because then who's ever using your function would be like, oh, I see this function only produces 1, 2, or 3. And so they won't have to consider any cases where it produces 4 or 0. So always, if there's the opportunity to be more precise with an any of, do so. All right. Now, the notes say that there are two other functions. There's add and remove, and we will leave that to you to do. I'm going to leave add for you to do. Now, you might be thinking to yourself, add is a simple function. All I have to do is cons an entry onto an association list. How easy is that? No, it's not. Yes, that technically adds an item to the association list, but there's one key thing we haven't mentioned about an association list, and that is that keys have to be unique. There can't be two students with the same student number. We wouldn't be able to differentiate you in our system. So an association list has the requirement that every key is unique, which means add is going to need to test for uniqueness before trying to add the entry to the association list. So I will leave that for you to try, but what I would like to do is look at how to implement removal from an association list. So, back over to Racket. Let's get rid of all that. Let's think about this first. If I want to remove an item from an association list, I'm going to do a lookup based on key. If the association list is empty, then the item isn't in it, so I should just produce empty. Now we always should write down some notes about our implementation before we actually write the function. Okay, we've handled the empty case. What if the current item, their key, that's the item at the front of the association list, has a key equal to the key I'm trying to remove? Well, then the answer in this particular case, we want to remove it from the association list. So this function remove is going to consume an association list and produce a new association list, which means that removing the first item, which is the item we're trying to remove because it has the same key, we should just produce the rest of the AF. There's no point in looking at the rest of the AL because we know that keys are unique. So if the first item in the AL is the one we want to remove, then we should just produce the rest. So we make just these little notes as we figure out each of the individual cases. This is how we plan, and then we're going to just plop our planning into the template, and we're done. Now, in the case where the keys are not equal, we know we need to keep the current item. So we want to keep the entry by consing that current entry onto the result of removing the item from the remainder of the association list. All right, our rough plan there, and now we can actually write the function, and it follows the template. There we go. Now we run this, we have no syntax errors, and now we can actually write some tests. Now I'm going to use the apostrophe list abbreviation. Please refrain from using it yourself until we specifically say you can use it. I just don't want to do that much typing. Yes, it does produce a list, but how it does it is different from cons and list. So let's say I want to write some tests for this. Now, I'm not going to write all of the tests, and I'm not going to write them as check expects, but I should check to make sure that if the item is in the list, it gets removed. So I want to remove key 2 from the list containing there. Hey, it worked. I also want to make sure that if the item isn't in the list isn't altered in any negative way. Now, this is not enough tests, but and it doesn't do it. So it works. Now, we would have to write a bunch of other tests. We'd have to do a test for empty. We'd have to do a test for the item in the list and a test for when the item is not in the list, and so on and so forth. All right. Any questions about this remove? Okay. Try add on your own. Now that's one way, one ADT we can work with. What if we wanted to work with multidimensional data? So for example, that was a list of key value pairs. What if now I want to work on, say, a grid of numbers or a matrix of numbers that is two-dimensional, so some number of rows and some number of columns? How do we actually do that? Well, that's just a list. If we just have a 2D grid, then that's just a list of lists, where each of the sublists has the same length. Because, of course, they all need to have the same number of columns. Now, how might we use this? Well, we might use this as a matrix. Or we might do something like try to create a multiplication table. And if you don't remember these, this is when you were like in grade 3, or I don't know when you might have learned them. They say, okay, you need to learn the 3 times table, and that is you need to learn what 3 times every number is. So you've got to do all the memorization. Okay. How do we create that multiplication table? All right. Well, what we see is that we're going to actually produce multiplication tables that are some number of rows followed by some number of columns. And something very important to point out about computer science is when we are counting, we start at 0. So if I want something that is 5 columns, the column numbers I have are not 1, 2, 3, 4, 5. They are 0, 1, 2, 3, 4. And if I want something that is 3 rows, then my row numbers are 0, 1, 2. So keep in mind we always start counting at 0. Now, what is going to be in each of the entries of my little multiplication table? It's going to be equal to the row number multiplied by the column number. So in this column here, this is column 0. That is going to be 0 multiplied by row 0, 0 multiplied by 1, and 0 multiplied by 2. And this box right here, number 6, that is going to be row 2 multiplied by column 3. So 2 times 3. All right. So how do we actually implement this function? Well, if you were to sit down and think to yourself, I'm going to implement a single function to do this, you would have the wrong idea. It's not to say it can't be done. It's just that it's much easier to subdivide this into smaller problems. Now, what I want to do first is maybe I should try producing the rows of this matrix first. Each row has a number, and the contents are that row number multiplied by each column number. So let's do the row production. And the template I'm actually going to use is the CountUp template. Now, this function is going to consume 3 different arguments. C is the current column number. This is what we are recursing on. So this is one of the natural number templates. R is the current row. We are producing the current row. That value will never change. NC is the number of columns we have to create. It is the base case. It does not change. Now, because we start counting at 0, when C is greater than or equal to the number of columns, that is our base case. And since we are producing a list, we produce empty. Otherwise, you can see here, I start with columns C equal to 0, and I want to get row 3 with 5 columns. So the first entry is 0 times 0. Sorry, 0 times 3, 1 times 3, 2 times 3, 4 times 3, 3 times 3, 4 times 3. And if I'm producing row 4, then this is going to be 0 times 1, or 0 times 4, 1 times 4, 2 times 4, 3 times 4, 4. We start counting at 0. So what does the function look like in the recursive case? Well, we are consing the current row number times the current column number onto the row I create by calling this function for add 1C. So if we were doing, if C was equal to, let's say 0 right now, this would be R times 0. And we're adding that onto the solution of 1 for whatever row and however many columns. Still simple recursion. We are always making exactly one step towards the base case. It's not too bad, right? So now we have a function to produce the rows. Now, or produce a single row. Now we need a function to actually produce all of the rows that we need. We'll follow the same template. So, in this case, we have 3 parameters. The current row number I am making, the total number of rows that there are, the base case for rows, and the total number of columns that there are. Only one of these we are recursing on, and that is R. And when R is 0, there are no rows to make, so we produce empty. Otherwise, I'm going to append the row that I am making onto the remaining rows. So the current row appended onto the result of creating the remaining rows. So I start with 0, I produce row 0. And then I'm going to produce row 1, and row 2, and row 3, and so on and so forth. Now, we need a wrapper function, because I can't give this to my user. They don't know what rows 2 is. They don't know what all these arguments are. What's this extra r parameter? What initial value should it be? So we make a wrapper function to wrap around this so that we are giving the user only the exact arguments that they need, which is how many rows and how many columns. We never want to assume that the user knows how to initialize this value here. So we have the mult table function. It just takes a number of rows and a number of columns, and it passes that through to the rows 2 function, and we start our out at 0. Cool. All right. Any questions about this one? One interesting thing about it I'd like to point out is in all of our previous simple recursion problems, how we combine item n with the solution for the n-1 items was usually something very simple. Cons, or add, or multiply, or something like that. And in this case, the processing we do to the nth item is actually a whole other recursive function itself. And so you might be led to believe this isn't simple recursion, but it is. And it's still simple recursion because each recursive step makes exactly one position closer to the base case. The other thing I want to say is that remember with simple recursion that we are only ever going to be modifying one of the arguments. There may be other arguments, but they cannot change. And that's true for this. All right. So we've seen a couple ways to use lists of lists. But all of the ways that we've used our list of lists, or our list so far, have all been simple recursion. Now we want to think more generally about how do I deal with functions that operate on 2 or more lists. Because they may break out of the bounds of simple recursion. So let's start with one that's still simple recursion. So my function consumes 2 lists, and it's going to append them to each other. What append does is it's going to put the first list on the front of the second list. So it makes a flat list made out of the 2 inputs. What's interesting about this is still simple recursion because we're only ever recursing on one of the lists. We're only ever going to recurse on the first list. If you look at it, some simple examples. If the first list is empty, and there are 4 cases to consider, if the first list is empty, then the result should be the second list. If the second list is empty, the result should be the first list. Obviously, if both lists are empty, the result is empty. And in a case where both lists are not empty, what you see here, so we have list 3, 4 and list 1, 2, 5, is you see we have 3, 4 and then 1, 2, 5. So we're going to put the first list onto the front of the other one. Okay. So how do we do this? Well, here's a simple solution. Even though there are 4 cases when you have 2 lists, there are only 2 you actually need to worry about. One is, if the first list is empty, we produce the second list. The second option is, if the first list is not empty, then we're going to add the first element of the first list onto the result of appending the rest of the first list onto the second list. At no point do we ever need to examine the items contained in the second list. Because how cons works is we are appending an item onto a list. And since we are trying to append one list onto another list, we only need to append each individual item of the first list onto the second list as a whole. So it's fairly simple. And by the way, you don't need to implement this. Append is a built-in function. do please be careful because we don't always allow you to use it. In fact, a lot of the time we don't let you use it. And when we don't let you use it, that doesn't mean you can go write your own. It means you need to find a whole different way of thinking about the problem. All right. That was fairly easy, I feel. We could trace through, and you could actually see how this works. So we have two lists, 1, 2, 3, and 4, 5, 6. And what we're going to do, and this is condensed, remember. So the first call is going to cons 1 onto the result of calling my append on 2, 3, and 4, 5, 6. The second recursive call is now consing 2 onto my append list 3 and 4, 5, 6. The third recursive call, now we have 1, 2, 3 onto my append empty list 4, 5, 6. And then in the last one, since the first list is empty, we simply produce the last list with the second list, and so we get our answer. So we can trace through. Okay, this is kind of boring though. Still simple recursion. I want something more interesting. So that was, we are using two lists, but technically speaking, the other lists were along for the ride. That is, they didn't actually change. Only one of the lists we were recursing on. Still simple recursion. What if I want to process two lists at the same time? We call this processing in lockstep. So when I'm accessing the first element of the first list, I should also be accessing the first element of the second list. And if list 1 is empty, so should list 2 be empty. So one of the requirements about lockstep is that the two lists actually have to be the same length. It's not too bad. Okay. Now this is not a simple recursion because we won't be recursing on one list. We're actually modifying two arguments. We're recursing on both of the lists at the same time. So, you might think that the template looks rather complicated. It isn't. It's a teeny tiny modification to the thing you've already seen. Now, because in lockstep we've made the rule or the requirement that both lists have the same length, that implies that if the first list is empty, so is the second one. So we don't need to check and list 1 empty and list 2 empty. We don't need to. We can assume that if list 1 is empty, so is list 2. So we just check, is the first list empty? If so, do something. Otherwise, both lists are not empty, so we're going to do something with the first element of each, and then we're going to combine in some way that result with the result from calling the lockstep template on the rest of both lists. So instead of just recursing on one list, now we're going on both of them at the same time. So when we are processing the fifth element of list 1, we are also processing the fifth element of list 2. You could write a function to test if two lists are equal, assuming they are the same length. You could write a function to add two equal length lists together. There's many different things that you could do. The example, however, we're going to show you is computing the dot product. So we can actually use a list to represent a vector. And the dot product is the sum of each element of the vectors multiplied together. So if we have 1, 2, 3, and 4, 5, 6 as our two vectors, it's 1 times 4 plus 5 times 3, or sorry, 2 times 5 plus 3 times 6. So it's these two elements multiplied and added to these two elements, multiplied and added to these two elements, and so on and so forth. Now, if this is not a function you're accustomed to, it's one that I use all the time. In computer graphics, we use dot products to do a great many things, but one of the most common things we use dot product for is to compute the angle between two vectors. And why do we want to compute the angle between two vectors? Well, I don't know. When the sphere hits the table, I'd like to know at what angle it should bounce off. Same thing, when the light hits the table, I want to know where the reflection should go. We always want to know the angle between the vectors, so we use dot product all the time. Very common function to use. All right. So we've seen the template. We should be able to fill it in now. We can do some test cases. So If we have two lists that are one element, we just get those two elements added, multiplied together. Otherwise, if the list has multiple elements, do the whole math thing. And then, what if the lists are empty? Well, if they have no elements, just produce 0. It's fine. It's totally fine. Fill in the template. If the first list is empty, then by our requirement of Lockstep, so is the other list, so produce 0. Otherwise, we add the first two elements multiplied together by the dot product on the rest of the lists. We are recursing on both lists at the same time, at the same rate. Any questions about this? Yep.
Is this also a simple recursion?
It is not simple recursion. So you could kind of argue that we will see this in the future, structural recursion or generative recursion. So there are lots of labels to recursion. Unfortunately, I refer to everything as recursion, but this is not simple. This is one of the ones. Okay. Not too bad, right? We can trace through it. I'm not going to trace through it. It's not going to bother. Okay. I do want to talk about a more complicated situation, though. We've done multiple list processing where we only ever recurse on one list. We've processed two lists together at the same rate. What if we want to process multiple lists at different rates? Now that one may not make sense to you. Why would we be recursing on two lists but at different rates? Well, before we look at some of the reasons why you might do this, I want to remind you of the different cases there's going to be. In the previous two kinds of recursion, we didn't have to think about all these cases because they didn't matter. Some of these cases actually merged together and became one case. Now that we're dealing with different rates, we may not be able to do that. So the four cases are, the two lists are empty, the first list is empty but not the second list, the second list is empty but not the first list, and both lists are not empty. 4 different cases. Once we think about those cases, now we can actually go and try to build our lovely template. So we put those cases in as the questions in our con. But you know what? This is starting to get really complicated. Because normally when we write our template function, it's very obvious which ones are our base case, and it's very obvious which ones are our recursive case. And in our recursive case, we know exactly which of the arguments we are doing recursion on. There's a lot of things for processing lists at different rates we don't know. For example, the first question is always a base case. Always. But is the second and third question a base case? Maybe. Maybe not. Maybe if we're done processing the one list, it's time to start processing the other list, and so we start recursing on it. So they may not be base cases. And what about the case where both lists are non-empty? How do we do our recursive step when both lists are non-empty if we're not processing the lists at the same rate? Are we going to recurse on both? Are we going to only move one towards a base case? Or are we going to remove the other towards a base case? It's an interesting question. So we could start to fill this in a little bit better. Empty stays the same. Now, in questions 2 and 3, where one list is empty and the other one isn't, they may be base cases and they may not be base cases. But we can cover that by just saying we're probably going to do something with the first of the list, and we're probably going to do something with the rest of the list. And we leave it as just ... not explicitly making a recursive call here because we don't know whether or not recursion is going to happen. And this ... in this particular case is indicating you could recurse, but you don't have to. What do you do for the last one? And you're sitting there and you're like, there's got to be an answer, right? The next slide has it. It doesn't. It doesn't have an answer because there isn't an answer. How would you do it? How would you actually indicate that you might recurse on this one, or you might recurse on that one, or you might recurse on both? That comes down to creating a template for a specific situation. So you are going to write a function, a template for a specific function. Well, if you are writing a template that only works for one function, why didn't you just write the function? The template then has no purpose because it's a single use. Templates are not meant to be single use. They're meant to provide you with a framework for a family of functions. And we find that it's very, very difficult to create a framework for a family of functions due to this last case here. Now, if you're sitting there thinking, is she going to ask this on an exam? I don't like this. And if I don't like it, I don't ask it. All right. That's the wonderful benefits of being the only instructor. All right. So, for the record, the next slide does illustrate some of the different options that there are, but kind of points out the fact that we don't know how to fill it in, so we can't. So let's actually do something now with two lists. Okay? One of the most common functions that we implement that processes two lists at different rates is called merge. And if you're familiar with sorting algorithms, this is one of the big steps to an algorithm known as merge sort. What we want to do is we take two lists that are sorted and we produce a single list that is sorted from them. So for example, told you I'm losing my voice here. If we have list 1, 8, 10, and 2, 4, 6, 12, we should get out another sorted list that contains every element in sorted order. Now you might be thinking to yourself, oh, so I got to call insertion sort on this after I append. Okay, technically speaking, that would work. You could append the list onto the other list and you could call a sorting algorithm. That's really slow though. What I really want to do is take advantage of the fact that I know both lists are sorted. And I could, if I'm clever, just create a sorted list as I process the two inputs. So maybe you're struggling to see how we might implement this, and if you're ever struggling to see how a function works, the number one piece of advice I can give you is to take a piece of paper and do some examples on it. Draw it out. Write it out. Do you see the patterns? And if you see the patterns, then you should be able to figure out how to write the code from that. So for this example, if I try to merge two empty lists, I know it should produce empty because I'm not merging anything. If one of the lists is empty, so say the first list is empty, then I produce the second list. And if the second list is empty, I produce the first list. Very easy base cases. But what about the cases where the two lists are not empty? So in this case, I take one element from this list, and then one element from this list, and then I take one element from this list. So we're going back and forth, back and forth. That's one way to do it. In this example here, this list is entirely preceding the other list. So I'm going to take this item, and then I'm going to append it onto this. Lots of different cases here. Well, let's look at the solution. Okay. Warning. This is ugly. This is hideous. This is disgusting. I understand, however, why they presented you the solution in this way. This is following the half-assed template that they have. But please don't write merge like this. This is terrible. But let's go through it. So if both lists are empty, we produce empty. There's no questions there. If, however, the first list is empty and not the second one, we just produce the second one because we don't have to merge anything. And likewise, if the first list is not empty but the second one is, then we just produce the first list because we don't need to merge anything. That's the very simple base cases. What about the cases where they're not empty? And And yes, it's hideous. It has a nested cond in it. Yuck. All right. So if both lists are not empty, then what we're going to do is we compare the first item of the first list to the first item of the second list. If the first item of the first list is less than the first item of the second list, then the item from the first list should be appended onto the front of the result of merging the rest of the first list with the second list. Otherwise, if the first item of the first list is greater than or equal to the first item of the second list, then I want to append the first item of the second list onto the result of merging the first list with the rest of the second list. So we are choosing which item to add to our list based on, is this one bigger or is this one bigger? Okay. It's really ugly, isn't it? How many of you would agree that the first two questions could be combined into one? See a couple of hands? Because they can. If the first list is empty, it doesn't matter what the second list is. You can produce the second list. Because if the first list is empty, and you produce the second list, and the second list is empty, then you produce empty, which covers the first case. And if it's not empty, you produce the non-empty list, and that's the second case. Furthermore, I don't need the and in there. I can just check if the first list is empty. So that's a whole pile of stuff we can get rid of. We can also get rid of this nested cond. So I'm going to open up my solution here for you to show you the difference. And of course, Racket, because it froze, I have to find it now. Okay. So it's just this first one here. All right. So what do you notice? I don't have any ands. I don't have a nested cond. Instead of like 8 or 9 lines of code, a nested cond and 4 ands, I have no ands and no nested conds and less lines of code. Okay, how does it work? If the first list is empty, produce the second list. We've already explained why that works. Otherwise, if the second list is empty, produce the first list. So we've now covered 3 of the 4 possibilities. And if both lists are not empty, instead of having a nested cond, I have a top-level question for you. So I check if the first item of the first list is less than the first item of the second list. And if it is, then I'm going to append the first item of the first list onto merging the rest of the first with the second. And if it is none of the above, the else, don't forget you have an else. They're great. Else, I take the first item of the second list and I attach that onto the front of merging the rest, or the first list with the rest of the second. It works the same as the other one. And we could prove it, because you got to prove that this stuff works. See? Works just fine. No problem. All right. Now, if you're sitting there thinking, I don't understand how she arrived at this answer so quickly, that's just probably because I've been programming in Scheme for 20 years. And I don't expect you to be able to arrive at this immediately. That template, the solution in the notes, that is a good first iteration. Let that be your first solution. And then come back and look at it and ask yourself, can I simplify this in any way? Look at the cases. think about, are these two the same? Is there some shortcut I can take here? Refine your code. You need to have a solution, but you shouldn't be trying for the best solution off the top. What you should do is get what you can, submit that, and then if you have time, refine it. Don't go for the refined version first. Now, from a human perspective, I would much rather see this than the solution in the notes. And I'm also going to tell you that technically speaking, this is also faster. Any idea why it's faster? Yeah? Because there's less steps to it. If you look at the solution in the notes, for each of the questions, I have to test empty and cons and AND it together. 1, 2, 3, just to get an answer to that question. My questions, empty, 1 step. Empty, 1 step. Less than, first, 3 steps, and then an else, 1 step. If you were to actually trace through this and trace through the ones in the notes, you will have significantly more steps from the version in the notes than here. Now you might be thinking, well, that's just me. That's just me tracing it out on a piece of paper. But what the heck did you think Racket was doing? It's doing the same thing you are, mostly. This is less work. Yeah?
You're not going to give us the example that's in the notes on that test, for example, right?
No, I don't want to mark that. Ew. So yeah, no, the version of merge in the notes is really, really long. And if I were to ask you to trace through that, it would, like, even for a small pair of lists, that would be like 3 pages of work. And number 1, that's a waste of paper. And number 2, I don't want to mark that. So yeah, no, I'm not going to ask you to trace through that. Should you know how to trace through it? Yes. If you can trace through merge, you're doing good. But I'm not going to ask something that long, because that's cruel for all of us. I think my worst marking story I've ever had is, it was another course, a 3rd-year course, and the professor who had written the solutions to the final exam left for a conference and forgot to give them to us. And so I had to, while the students were writing the exam, I wrote the exam to get the solutions, only to realize one of the questions took us, I think, 10 days to grade. Never again. If we can't have these midterms marked in 1 day, that's what I call a nightmare. So no, I'm not going to ask you to trace through something that takes 20 pages. That's cruel for all of us. All right. So, there's an example of tracing through this in the notes. Again, this is a condensed trace. You're welcome to trace through this on your own, but I'm not going to trace this for you. Now, I know there's still like 5 minutes left of class, but my voice is almost gone. And I'd like to preserve a little bit of it so I can, yell at my kids for jumping on the couch. So pretend it's the early weekend and go home and watch movies or something.